Assalamu alaikum, dear student. Today is the lecture number 1 of week number 5, and today we are going to study the fluid kinematics, and the learning objective of the fluid kinematics are discuss the differences between the Eulerian and Lagrangian description of fluid mechanics that you will be able to discuss and understand after completing this chapter, and you will also be able to identify various flow characteristics based on the velocity field, and also you will be able to determine the streamline pattern and acceleration field given a velocity field, and also you will be able to discuss the differences between a system and control volume, and finally you will be able to discuss and drive the continuity equation. So let's see, the topics we are going to cover today are the fluid kinematics. Definitely we will discuss the introduction and Eulerian and Lagrangian approach of fluid flow, Eulerian description of velocity, acceleration field on and material derivatives, flow pattern, and finally the we will drive a equation, that is continuity. Let's see what is fluid kinematics. The fluid kinematics is the study on fluid motion in space and time without considering the force and moments which causes the fluid motion. So in the fluid dynamics there is the another component of the fluid dynamics, that is fluid kinematics. In fluid kinematics you know that we describe the motion by displacement, velocity and acceleration. So in kinematics we will discuss only about the displacement, velocity and acceleration, and we do not discuss the cause of displacement, velocity and acceleration. So here we will talk about the velocity field, we will talk about the position vector, we will talk about the acceleration field. Okay, so in general, fluid flow means a net motion of a fluid molecules from one point in space to another point in space as a function of time. So a small portion of a fluid contains so many molecules, and it is not realistic to account the motion of individual molecules. So you should understand, you see, the fluid has a millions and trillions of molecules. Okay, so you cannot discuss a single molecule, because if there is a pipe, there are so many. If there is a fluid flow in the pipe or there is a gas flow in the pipe, so you can understand how many molecules are there. So we cannot observe or discuss every single molecules in it. Okay, this is totally different than the solid. So instead of that, we talk about the group of molecules. Okay, that indicates the behavior of the total fluid flow system. Therefore we assume that the fluid is made of a fluid particles. Each fluid particles contains numerous molecules. So we describe the fluid flow in terms of the motion of fluid particles. Okay, so this motion is described in terms of velocity and acceleration. At a given instant of time, the velocity of each particle of flowing fluid is different in both magnitude and the direction. Okay, so this is very important point to know, that at a given instant of time the velocity of each particle of fluid is different in both magnitude and direction. So here you can see this is a particle A at time t. So at time t, this is the position of the fluid particle, and after time t plus of delta t, the position of the particle changes. Okay, so it is indicated with, so the position is of a velocity is subjected to the time. So we can say that both magnitude and direction are different of a particle as the time changes. Now the primary dependent variable is fluid velocity vector. V is the function of position vector, where R is the position vector. Okay, so let's move on to the next slide. So here, so if V is known, then pressure and force can be determined using technique to be discussed. Okay, if you know the velocity, then we can find the pressure forces, pressure and other forces, okay, by using different techniques that we will study. So consideration of velocity field alone is referred to as a field kinematics. Okay, so whenever we talk about the effect of force only, that is referred to a field that is kinematics, in distinction from flow field dynamics, force consideration in the fluid dynamics. Okay, so now we are going to discuss the two different approaches, that is Eulerian and Lagrangian approach for the fluid flow. So what are they and how they are different from each other, and when they are useful to apply. So Eulerian and Lagrangian are the two approaches generally used to describe the fluid motion. In Eulerian approach, the properties of fluid motion, pressure, density and velocity are prescribed as a function of space and time. Okay, so all the fluid properties and the flow properties, okay, the fluid properties are pressure, density, viscosity, okay, and surface tension. These are the fluid properties, and the flow properties are the velocity, the acceleration, the position. These are the flow properties. In the case of Eulerian approach, okay, in the case of Eulerian approach, these flow and the fluid properties are described as a function of space and time. Eulerian approach provides information of fluid flow at a fixed point in space. We will discuss about it with an example. Okay, so Lagrangian approach follows the trajectory of fluid particles. It provides the properties of fluid motion as riding on the fluid particles. Okay, so the difference you can understand now. Okay, for the Eulerian approach, we observe the flow and fluid properties at a fixed points in space. Okay, in the Lagrangian approach, we follow the trajectory of the fluid particle. It provides the properties of fluid motion as riding on that fluid particles. Okay, so let's see an example of the smoke is discharging from a chimney. Okay, so how we can apply the Eulerian and Lagrangian approach in the same cases and how they are different. So in Eulerian approach, one may attach a temperature sensor to the top of the chimney and record the temperature at that point as a function of time. So here we have attached a sensor. So whatever the smoke is exiting from the chimney, we are measuring the temperature, okay, as a function of at this point, okay, at time t, at time t is equals to 1 second, time t is equals to 2 seconds or 3 seconds. So whatever is the fluid particle passing through it, we are measuring the temperature. If you want to measure the temperature of this point, so you can put another sensor here so that you can record after time, record from here. If you want to measure the temperature of the fluid after passing here, you can do like here. If you want to measure the temperature of the fluid particle which are passing from this area, you can put a sensor here. So this is the Eulerian approach. In the Eulerian approach, we put a sensor in a particular position, okay, and from that position we observe or measure the fluid or flow properties data, and based on that we do our analysis. So at different times, okay, here at different times there are different fluid particles passing by the stationary sensor. The use of numerous temperature sensors fixed at a various location can provide the temperature field. Okay, so in the Lagrangian approach, we put the sensor at a different position, and from those position we measure the temperature, pressure, or whatever the fluid or flow properties you needed. So in Lagrangian approach, one may attach the temperature sensor to the fluid, to a particular fluid particle, and can record the particle temperature as a function of time during its motion. So here you can see we consider a particle and we put the sensor on the particle. So at every time, so here the temperature is a function of time, but here the temperature is a function of position, because the position of the sensor is defined and what time we are measuring we are calculating. But here at time t, wherever this particular particle is going, we are measuring its temperature with respect to time. Okay, so if you want to notice because one fluid particle, the smoke has millions and trillions of molecules. So how many fluid particles you will put how many sensors you will put on them to take the temperature of each fluid particle. So here you can see the use of many temperature sensors moving with different fluid particles can provide the temperature of these fluid particles as a function of time. Okay, so the temperature would not be known as a function of position unless the location of each particle is known. Okay, so if enough information in Eulerian approach is available, the Lagrangian information can be derived from the Eulerian data and vice versa. So we assume that, or based on the analysis, the Eulerian approach is more easy and effective. Okay, but in some cases the Lagrangian approach are very important. For example, if a fish moving in a fluid in a sea or in a river or in a pond, so if you want to observe that particular fish, so you can put sensor on it and you can take its behavior. Okay, so in that case, that is the Lagrangian approach. If you want to observe an animal in a jungle, so you can put a camera on it and you can take you can monitor its movement, its behavior, whatever you like. So that is basically the Lagrangian approach. But the Eulerian approach is something different that we have already discussed upward. So in fluid mechanics, it is easier to use the Eulerian approach to describe the flow. So I believe you can understand the Lagrangian and Eulerian approach. So let's move on to the next slide. So now the Eulerian description. So what is the Eulerian description? In Eulerian description, we describe the velocity, acceleration, and the fluid properties, pressure and force and all as a function of space and time. So here the Eulerian description of fluid flow: a flow domain or control volume is defined by which the fluid flow in and out. So what is the control volume? Control volume is the volume, okay, through which we observe the fluid is entering to that particular volume and exiting from that volume. Okay, so that means that is a specified volume. Out of that volume, we do not observe the behavior of fluid flow or the fluid properties. So here we define field variables, okay, which are function of space and time. So field variables may be temperature, may be pressure, okay, may be viscosity, may be density, or could be any fluid properties, or it can be velocity, it can be acceleration. So in the Eulerian description, we describe the fluid properties and the flow properties in terms of space and time. So here you can see, if V is known, then pressure and force can be determined using technique to be discussed. So here the pressure field. So pressure, we know that it can vary in all direction as well as it can vary with time. So here we are describing the pressure in the form of Eulerian description. So here we are describing the velocity in the form of Eulerian description. Okay, so v as a function of space coordinates as well as the time. Okay, so we can, so here you see this the point 1 and this is the point 2. Okay, this is the position vector. The position vector can be written in the form of vector, that is xi, yj and zk, in the form of Cartesian coordinate. Okay, and this is the velocity vector. Velocity vector is the function of space coordinate and time. Okay, the velocity vector is the function of space coordinate and time, and it can be written as the ui, vj and wk. So the velocity in the x direction, okay, the component of velocity in the x direction, that is u, the component of velocity in the y direction, that is v, and the component of velocity in the z direction, that is k. So here we describe the Eulerian description of velocity. So this is, that means u is the function of x, y and z and time. V is also the function of x, y, z and time. Okay, so now the acceleration field can also be described. Okay, so here the acceleration in the x direction is the function of space coordinate and time. Acceleration in y direction is also the space coordinate and time. So here we describe the acceleration field in the form of Eulerian description. So these and other field variables define the flow field. Okay, so these velocity, acceleration, position vector, these basically define the flow field. So let's solve an example. So I study two-dimensional velocity field. So I study incompressible two-dimensional velocity field is given. So this is the velocity field is given, the two-dimensional, the w factor or the k factor is ignored. Okay, so here where x and y coordinates are in meters and the magnitude of velocity is in meter per second. So we will discuss later what is one-dimensional flow, what is two-dimensional flow and what is three-dimensional flow. Okay, incompressible you already know where incompressible flow you already know where the density is constant. Okay, so a stagnation point is defined as a point in the flow field where the velocity is 0. Okay, so this is the definition of the stagnation point where the velocity is 0. So we will discuss later on what is the stagnation pressure or stagnation point, we will discuss later. So determine if there are any stagnation point in this flow field. Okay, if so, where we have to determine the coordinates. B, sketch the velocity vector at several locations in the domain between x is equals to -2 to 2 meter and y is equals to 0 to 5 meter. Qualitatively describe the flow field. So we have to determine the magnitude and we have to drive the graph or sketch within this range, okay, of the velocity field. So first of all, the velocity field is given. Okay, so we have to determine the velocity in the x coordinate and y coordinate. So v is the function of u and v in the x and y direction. So this is u and this is y. Okay, sorry, this is v, this is u, the velocity in the x direction, this is v in the velocity in the y direction. Okay, so here u is equals to this and y is equals to this. Okay, so if you simplify it, okay, so here the stagnation point is the point where the velocity is 0. In v is 0, that means both component will be 0. So the stagnation point you can calculate. So x is equals to point this minus 0.6.25 and y is equals to 1.875. Okay, so this is the stagnation point where the velocity will be 0. Okay, so there is one stagnation point located at x is equals to 0. So it is confirmed that there is a stagnation point at x is equals to 0 and y is equal at x is equals to minus 0.625 and y is equals to 1.875. And second, now we have to sketch the velocity vector in several location within this domain which is given. Okay, so let's see. So here this is the function is given, and here is the you can see this is the range from minus 2 to plus 2, and this is from 0 to 5. We have to scale 1 is equals to 10 meter per second. Based on that, you can take any other scale suitable to you, and then put different value of x and y and calculate the v, and describe here the point, and later on join all the points so that you can get a line that is called a velocity field. Okay, and this is also called a velocity field or the streamlines. Okay, so if you plot like this different points, x is equals to this, y is equals to this, then you will get a line, and then again second and third you will get in this way. Okay, so let's see how what are these lines are indicating. So velocity vectors for the velocity field of example 4-1. Okay, the scale is shown by the top arrow. There is the scale, you can choose your own scale, and the solid black curve represent the approximate shape of the sum streamlines. So these lines are approximated. You took 4 or 5 points and you join them together, and based on that other lines you join them together. Okay, so based on the calculated velocity vector, okay, the stagnation point is indicated by the circle. So this is the stagnation point where x is equals to minus 0.625 and y is equals to 1 point something. So this is the stagnation point, okay, which is indicated with the circle that we calculated here. Okay, so here you marked it. The shaded region represents a portion of the flow field that can approximate flow into an inlet. Okay, so this is the approximated line where there is an inlet. This is the exit. Okay, this is the discharge. Okay, so this is the approximated point. Okay, so you can draw these line by taking x is equals to this component, y is equals to this, you can draw. Okay, so and the range it's given to draw, that is minus 2 to plus 2, and from 0 to 5 you can do that. Okay, so let's see here the next topic, that is acceleration field and material derivative. Okay, so the acceleration of a fluid particle is the rate of change of its velocity, that we all know. Okay, so in Lagrangian field how the acceleration field can be represented, and in Eulerian approach how the acceleration field can be represented. So you know that in Lagrangian approach the velocity is the function of time only, and the position vector is the function of time only. So in Lagrangian approach the velocity of a fluid particle is a function of time only, since we have described its motion in terms of its position vector. Okay, so here it is the function of time only. Okay, so if you take the derivative, so you will get the velocity, so that is u of the particle, v of the particle, and omega w is the particle. So if you take the second derivative, so you will get the acceleration of the particle. So it is the function of time only. Time, rate of change of velocity in the x direction, y direction and z direction will give you the acceleration in x, y and z direction. So acceleration in the x direction will be equal to du particle over dt, d vp over dt. In the acceleration in the z direction, dwp over dt. So here the acceleration is only the function of time. Okay, so now let's move on to the Eulerian approach. In the Eulerian approach the velocity is a function of both space and time, such that, okay, so velocity is the function of x, y, z and time. Velocity is the function of, in the v is the function of position and time, w is the velocity of position and time. Okay, so where u, v, w are the velocity component in x, y and z direction, and x, y, z as a function of time. Okay, the position is a function of time, since we must follow the particle in evaluating dv by dt. Okay, so if you take the derivative of this, so what will happen if you take the derivative dv by dt? So du over dt is equals to I, dv over dt over j, dw over dt over k. So this is going to be ax, ay and ak. So this ax, ay, aj, ak is not that simple. Okay, here you can see, so ax will be equal to du by dx. Okay, it's a total derivative, and u is the function of space coordinate as well as time. So when you have it is the function of space coordinate and time, then you have to take the partial derivative. When you take the partial derivative with respect to space coordinate and time, so it will open up like this. Okay, so first of all, the velocity in the x direction with respect to time, and then plus velocity in the x direction with respect to change in velocity with respect to x, and del x over del t, then in y direction, and then in z direction. So in Eulerian approach, the acceleration is equal to this is the complete factor, while in the Lagrangian approach this is the only factor of acceleration in the Lagrangian approach, because this is only the function of time, but here it is the function of time as well as function of space coordinate. Okay, so where del x over del t, del y over del t, del z over del t are not arbitrary but assumed to be following the flow field particle. So del x over del t is equals to ui. Okay, if it is x, it is y, it is j. Okay, so let's see. So ax going to be del u over del t, so that is basically u. So del u by del t is equals to u, del u by del x, and del y over del t is equals to v, as we say that here. You see this is this is equal to u, this is equal to v, this is equal to z. Okay, so because this is the velocity in the x coordinate, y coordinate and z coordinate. So here, so x will be equal to this, and this is called substantial derivative. Du and dt is called the substantial derivative. Similarly, ay and z can be written in the same form that we have written previously. It is in the ax we have written in this form. Similarly, ay and az can be written in this form. So if we simplify this, okay, if we simplify all three factors, because ax, ay and az, when you will insert this value here, when you insert this value here, you will be end up with del v over del t. Okay, because here del u by del t, and then in the y component you will get del v by del t, in the z component you will get del w by del t. So del u by del t, this all equal to del v by del t. Okay, because v is the function of space coordinate and time, plus v dot into del v. So what is del operator? We already know that is the gradient operator, and it can be written like this. Okay, it can be written like this in the vector form. So here the first term del v over del t, called local or temporal acceleration, results from velocity changes with respect to time at a given point. Local acceleration results when the flow is unsteady. Okay, we will discuss what is steady and what is unsteady. If the flow properties and the fluid properties are changing with respect to time, okay, such flow is called a steady flow. If the flow properties are changing with respect to time and position, such flow is called unsteady flow. Okay, so del v by del t is, that means the velocity, if the velocity is not changing with respect to time, that means the flow is steady. If the if the velocity is changing with respect to time, the flow is unsteady. So If del V by del T is equal to 0, that means flow is steady. The second term, del by del V, called the convection acceleration, because it is associated with the special gradient of the velocity in the flow field, because these are the function of space coordinates. Okay, if this is the function of time, this factor is the function of time, and this part is the function of space coordinate. So this is the component of acceleration due to the space coordinate, and this is the component of acceleration due to the time. Okay, so convection acceleration results when the flow is non-uniform. That means the velocity is changing with respect to space coordinate in x, y and z direction. That is, if the velocity changes along a streamline. Okay, the convection acceleration terms are non-linear, which causes mathematical difficulties in flow analysis. Also, even in steady flow, the convection acceleration can be large if a spatial gradient of velocity are large. So this is a very important point to know. You see, the convection acceleration results when the flow is non-uniform, is the flow is non-straight line. Okay, that means the space coordinates x, y, z are changing. If it is changing, definitely the line will not be straight, it will be different, a different shape. Okay, but if the velocity, if the flow is uniform and steady, that means the streamline will be a straight line. Okay, so let's move on to the material derivative. What is the material derivative? The total derivative operator d by dt in this equation is given a special name, that material derivative. Yani we are calling this d by dt. Okay, we have derived already the acceleration. Okay, and we end up with these two components. This is the local acceleration and this is the convective acceleration due to the space coordinate changes, and this is the due to time changes. So we are calling this d by dt with a special name, that is material derivative. It is assigned a special notation, capital D by dt, in order to emphasize that it is formed by following fluid particle as it moves through the flow field. Okay, other names for the material derivatives include total derivative, particle derivative, Lagrangian or Eulerian derivatives, and substantial derivative. Okay, so it can be seen how the fluid particle is changing with respect to time. So the material derivative d by dt is defined by following fluid particle as it moves throughout the flow field. Okay, so that can be described with this material derivative. The position of a fluid flow is can be described with this derivative. Okay, okay, in this illustration the fluid particle is accelerating to the right and up. Okay, it is also accelerating to the right and as well as up, so it's going to be a two-dimensional changes. Okay, so material derivative can be written in this form. Okay, so this is small d by dt is changed with capital D by dt, and this is called material derivative, and it can be written in this form. Okay, so material acceleration. Okay, if you are considering a flow field or the velocity vector, so if you are writing a velocity vector, so it's going to be acceleration field. If you are putting a pressure here, so it's going to be material derivative of pressure. Okay, so whatever is the component here, that going to be a material derivative. If temperature you are taking here, the material derivative of temperature, material derivative of velocity. So this is how you are explaining this. So this is called a material derivative, this is called the local derivative, and this is advective derivative. The material derivative is a component of local or unsteady part of a convective or advective part. Okay, so here is the explanation of the material derivative. Okay, so now we can go for one example. Okay, material acceleration of a steady velocity field. Okay, steady velocity field means the change in velocity with respect to time is 0, but the change in the convective acceleration is not 0 because it can be changed with respect to the position vector. So consider the steady incompressible two-dimensional velocity field of example 4-1. Calculate the material acceleration at the point x is equals to 2 meter and y is equals to 3 meter. Sketch the material acceleration vector at the same array of x and y value in example 4.1. Okay, using the velocity field equation 1, example 4-1, and the equation for material acceleration component in Cartesian coordinates, because the values are given in the Cartesian coordinates. Okay, so here you are saying the previous example that we have solved, we should consider the same function of velocity vector and to calculate the material acceleration. So we have to calculate the material acceleration by using this same function. Okay, same velocity function. Okay, so we write expression for the two non-zero component of the acceleration vector. So what was the acceleration that we calculated? What was the acceleration function that we know? This is the acceleration, this is the velocity function that is given. So we are going to use the same velocity function in this problem. So here you see, so ax, the velocity, because it's a two-dimensional velocity function, so this is ax and ay. So ax is equals to del u over del t and u del u by del x plus v del u by del y and w del u by del z. Okay, so here the since flow is steady, so del u by del t is 0. So this is the values are all known. Okay, we solve it and put it. This is the values are all known, we solve it and put it. The z component is, since w is 0, so all the factor will be equal to 0. When we solve it, finally we end up with ax is equals to 0.4 plus 0.64 Okay, now the y component of acceleration we open up in the same way. So we insert the value and finally we get this value. So at that point x is equals to 2 and y is equals to 3. So if x is equals to 2 and y is equals to 3, so what is the value of ax and what is the value of ay? So I put the value of x is equals to 2 meter and I got the value of acceleration. I put the value of y here and I got the acceleration in the y direction. Okay, so this is the value of x and y. So let's move on to the flow pattern. The fluid mechanics is a highly visual subject, okay, because definitely we visualize the physical behavior of fluid. The pattern of the flow can be visualized in a dozen different ways, and you can view these sketches or photographs and learn a great deal qualitatively and often quantitatively about the flow. Okay, so what is the behavior of the fluid flow that can we photograph, or now the special technology, the CFD. Okay, by putting those values we can develop the behavior of the flow pattern. Okay, 4 basic type of line patterns are used to visualize flow: a streamline, a path line, a streak line, and a timeline. So what is a streamline? A streamline is a line everywhere tangent to the velocity vector at a given instant. A path line is actual path traveled by a given fluid particle. Okay, a streak line is the locus of a particle that have earlier passes through a prescribed point. Okay, timeline is a set of fluid particles that forms a line at a given instant of time. So let's go and see in little detail. So here you can see a streamline is a curve that is everywhere tangent to the instant local velocity vector. So consider an arc. So consider this is an arc. Okay, at every point this is the position vector of the arc and this is the velocity which is tangent to the arc. Okay, so both are in a same direction. So if you make a right angle triangle, so this is the right angle triangle for the position vector and this is the right angle triangle of the velocity vector. So the velocity component in the x direction is u and the velocity component in the y direction is y. So this is the position vector and this is the velocity vector. So geometric arguments results in the equation for a streamline as illustrated in the figure. Okay, so we can develop an equation for the streamlines. For two-dimensional flow, the slope of the streamline dy by dx. So what is the slope of the streamline? Dy by dx must be equal to the tangent to the angle that velocity vector make with the x-axis. Okay, so we can equate those right angle triangles and finally dy by dx will be equal to v over u, and in 3 dimension we can write down dr over v is equals to dx over u, dy over v, and dz over w. So this is the equation of a streamline. Okay, and these lines are indicating as a streamline because the velocities are tangent to the streamline at every point. Okay, the velocities are tangent to the streamline at every point. Such lines are called streamlines. Okay, you go through the stream tube what exactly it is. So let's move on to the path line. The path line, the actual path traveled by an individual fluid particle over some time period. Okay, so a path line is a Lagrangian concept in that we simply follow the path of an individual fluid particle as it moves around in the flow time. Thus a path line is the same as the fluid particle material position vector. Okay, so definitely the path line is the line at which we can use a Lagrangian approach. So a particle in time t or any time travel from one point to another point, it describe its way. Okay, so such line followed by a single particle is called a path line. Okay, so streak lines, the locus of a fluid particle that leaves passed sequentially through a prescribed point in the flow. Streak lines are the most common flow pattern generated in a physical experiment. If you insert a small tube into a flow and introduce a continuous stream of tracer fluid, dye in water flow, or smoke in a air flow, the observed pattern is a streak line pattern. Okay, here you can see at every small time t, this is the first particle came at time t, and then after time t another particle came out, then another particle came out after time t, then another particle came out after time t. So the interval is same. Okay, but the position of the particle that leaves from this point at time t are different. So when we join all those points, okay, these points are called streamline. So these streak lines. These lines are called streak lines. Okay. So let's move on to the. Okay, here you can go through these points. This we have already discussed. Okay, the streak lines. So this and remaining part of the lecture I will describe the continuity equation and one-dimensional flow I will describe during the live session. So please watch this video, that will help you very well to clear the concept of streamline, streak line, path line and timelines. So this is all for the today's lecture. Thank you very much. Assalamu alaikum.